Welcome back. This final problem I have on the related rates handout here is actually giving me a little bit of PTSD because this is actually very, very close to one of the things I had to know how to do on that horrible Indiana teacher's exam thing. And so let's work it through together and try not to develop any flashbacks or anything like that from that bad time. All right, what the problem is showing here is there's a cone-shaped tank that they're filling up with water. So like water is somehow filling in, and right now it's this high up. And it's filling up at a rate of 12 cubic meters per second. That's a hell of a fast way to fill up a tank. 12 cubic meters is a lot of water per second. Okay, so the change in volume of this part of the tank here, the part where the water is 12 meters per second. They give us in the problem some other details about the shape of the cone that we're filling up. For example, the radius of the top of it here, of this cone-shaped piece, is 26 meters, which is, like a swimming pool. And the height of the cone is 8 meters. You'll notice, as I said on there, this drawing is nowhere near to scale. The real cone would be this really, really wide thing that is hard to draw. But okay, so the cone is 8 meters deep. Right now it's actually only H meters deep because we were just worried about the height of the water so far in there. At the present time, it tells us that the radius of the water in the top of the cone here is 10 meters. So we have water, let me just draw in here. It's like this part of the tank is currently full of water. Okay, and it says, at what rate is the depth of the water of the tank changing? So what we want to find here is dH dt. All right. The change in rate of the depth of the water at this particular time. When the water has a radius, the top of its cone here has a radius of 10 meters. The tank is being filled at a rate of 12 cubic meters per second. All right, we've got all this good stuff here. Now, when I first started doing this problem, I couldn't figure out why they were giving us all this other information about the tank. What does it matter how tall the tank is and so on? But you're going to see that doesn't really affect, that helps us with our problem here. So we've made our diagram here. Related rates problems, especially the story problems, it pretty much always makes sense to make ourselves some kind of diagram here. Now, on your handout here, I deliberately went down the wrong path for a while, and I'll let you work through, right here below that diagram that I drew. That actually I stole off a website. I went through a couple steps here that only made things worse. And I did that on purpose, believe it or not, because I wanted to show, the obvious thing of first immediately taking the derivative actually made things worse. Because then we'd have to know dr dt, which there was nothing in the problem that was helping us do. We actually needed 3 different related rates, and generally speaking, that's not the direction we want to go on to. We only want to end up with 2 related rates, d something dt and d something else dt. If you have 3 related rates, the problem gets way more complicated, way faster. So I won't go through all those steps. You can look through those for you. Instead, what we're going to do is think back to what we did with that problem of the guy walking toward the lantern or the lamp or whatever it was. And we're going to think about this again and realize that there are some similar triangles here so that we can get rid of the value of r. I want you to notice that there's 2 similar triangles here. There's this triangle that makes up this sort of big piece that describes the tank. And there's this little triangle that describes the part of the tank that currently has water in it. And they are similar triangles, similar again in the sense of geometry, like they have the same angles, they have, their sides are proportional to each other, and so on. And so we could use the similar triangles to say, hey, this r that we have, wherever we are right now in the tank, however full we are, the r that describes the radius of the top of the water has a ratio to the size of the tank as the depth of the water has to the depth of the tank. This side of the triangle's ratio to this side of the triangle is equal to this side of the triangle's ratio to this side of the bigger triangle. Again, those similar triangles are often kind of a tricky thing to find. You have to start looking for the patterns in these problems. But it's unsurprising that what we have found here is a way that relates the depth of the water, h, to the radius of the water on the top. And in fact, this is pretty neat because we can then pull over that 26, r is equal to h times 26 over 8, which is the same thing as 13/4 h. But what this has given us here is a way of relating r and h, or a substitution we can make. We can get r out of this problem. That's a great idea. See, we want to know the volume. The volume of a cone, which is 1/3 pi r squared h. But we can get rid of the r now because we have a substitution we can make for that. That's 1/3 pi. Instead of r squared, we could have 13 over 4h squared times h. See how I got rid of r? There were too many variables originally in our equation, and we took that wrong path that I described here in the handout. We had too many variables in this equation. R's and H's and stuff. I got rid of the r. Okay. This is pretty messy here. This 1/3 pi r, this will be 169 over 16h. But with a little bit of rearranging here, you can work through on the handout if you want to. You can see this works out to 169 over 48 pi h cubed. Hey, I've got a helper here. Gabriel's here. Hey, Gabriel, I'm teaching right now. Can you go downstairs and watch George?
Okay.
Okay, bye. All right. All right, so now we have a way of describing the volume only based on how deep the water is in the cone. That makes it pretty simple. Now we only have one variable on each side. We can just take the derivative of both sides. The derivative of the left-hand side is the change in volume with respect to time. The other side will be, the derivative is 3h squared dh dt by implicit differentiation. All right. What we are trying to find, according to the problem, is dh dt. We are actually given dv dt. That's just a 12. H, all right, we are getting pretty close here. In fact, if we just rearranged all this, pulled the stuff over to the other side here, it's ugly. It's dv dt all over 169 over 16, because some of these numbers are canceled. 16 pi h squared equals dh dt. All right, we have dv dt, that's just 12. This is just a horrible fraction. That's just pi, but we don't actually have h yet. But actually we had a way to compute h. I mean, if we just go back right here, we know at this time r is 10. So we could just work through and find the value of h from this. At this time, h turns out to be 40 over 13. Okay, you're going to just plug those numbers in over here, pull that 8 over to the other side. It's 40 over 13. And when you plug that in to the h, and you plug that dv dt that we were given in the problem, you get the strange number of, oops, that's not right, 3 over 25 pi. It's just plugging in now and simplifying fractions. A whole bunch of stuff will simplify pretty straightforward because, well, that 13 will become 13 squared and it'll cancel over here. It actually isn't so horrible once you start doing the numbers. So we found our answer here. The rate of change of the depth of the water in the cone was this number, 3 over 25 pi. At that point. Obviously that only depends, though, at that particular time. Later, as we get deeper in the cone, this number will be smaller, because we're filling up a wider place. Down here at the bottom of the cone, when we filled it quickly, when we were adding 12 meters cubed per second of water, we filled the bottom of the cone real fast. But obviously, as it'll get slower and slower as we fill up towards the top of the cone. Cool. Huh. Certain kinds of rain gauges work that way, by the way. A type of rain gauge called farmer's wedges. I'm just having flashbacks to something else that was on the math test. All right. So you now have seen 5 examples of related rates problems in addition to the ones that you had due today. Now, on Google Classroom, you have the problems for today. These will be due on Wednesday, the 18th of March. There's only, I think, either 3 or 4 of them, not very many. And then there's an exit ticket. I think the exit ticket only has 2 problems on it. Then there's a couple questions I just have about how everything's working with this whole being out of school thing. Okay. So you'll take care of those things, and what I'm really looking forward to is your questions. Don't wait until like late Tuesday night or early Wednesday morning or something to get these guys done, because you're almost certainly going to have questions that I will be excited to get. All right. So please let me know what you have questions about. Please take care of yourselves. Stay on track. Don't get behind on your classes. And let me know if you have any questions.